Good afternoon. This is Professor David J. De Los Reyes. My topic this afternoon will be Bernoulli's equation. It's a continuation of the Bernoulli's equation topic that is under my differential equation course. Okay, let's proceed, guys. This is now lesson number DE29 on my differential equation course. The subtopic is Bernoulli's equation. I think this will now be equation, example number 3 on the evaluation of problems under Bernoulli's equation. Bernoulli's equation number 3. Okay, let's proceed. This is another evaluation problem. So for you guys who are taking differential equation, this is for you. The given differential equation is x dy minus y dx equal to x cubed y to the fourth dy. We are asked to find the GS, general solution. Okay, let's try to bring out the solution. I will try to make the explanation concise and very short so it is easily understandable. This is a long video, guys. This is not a short video. So I will have all the time to explain the step-by-step details. Okay, let's proceed with the solution. We are given this differential equation. I will try to expedite a little bit. If we try to rearrange this one, we will try to solve for dx over dy. Okay? It might take 3 steps, but if we try to rearrange this and we try to go to the form dx over dy, what will come out will be dx over dy plus 1 over 2y times x equal to, the right hand side will be negative y cubed over 2 times x cubed. That is after the rearranging. I expedite a little bit. I didn't show you the steps, but that's just algebraic manipulation. So if we try to rearrange this one, what will come out will be this. And if we try to observe the resulting rearranged differential equation, this is similar, symbol for similar. Dx dy plus r of y times x equal to s as a function of y times the value of x to the n. So actually this falls under case number 1 under Bernoulli's equation. There is an x to the n over here because without the x to the n, it now falls under the solution by using ASAP integrating factor. But since there is an x to the n on the right hand side, okay, it's a must that we shall solve this one by using Bernoulli's equation. And it falls under case number 1. For case number 1, the value of n is actually 3. Right? And there is a needed substitution. The needed substitute is actually z equal to x raised to 1 minus n. We now know n. So by following this equation, we will solve for z as a function of new n. New x, well, so z now will be x raised to 1 minus 3, z will be x to the minus 2, or z is equal to 1 over x squared. We eliminate the negative thing, we bring it down, so z is actually 1 over x squared. And if we try to compute for x over here, x squared is actually 1 over z. To solve for x, without the power 2, we raise both sides of the equation by 2. So these two here cancel with this. X now will be, the square root of 1 is just 1, and the square root of z is just the square root of z. It is this. Okay? So we now know the value of x in terms of z. We needed the equivalent to simplify the solution. So if we try to take the differential of both sides, dx is actually negative dz over 2 z to the 3 halves. Actually, we could compute for dx by using the power formula. because x is actually z to the minus 1 half, right? So if we try to compute for dx, it will be negative 1 half times z raised to minus 1 half minus 1 will be minus 3 halves times dz. Or if we try to simplify this, we bring down this 1. Okay, so this will be negative 1 times this, it will be negative dz. We bring down this 1, this is 2, there's a 2 over here, z to the 3 halves. It is this. Okay, it's the power formula under differentiation. I expedite a little bit, but I show you how it was derived. So dx is actually minus dz over 2z to the 3 halves. So if we try to compute for the value of, substitute the value of dx and the value of x, we place it here. So I place it here, substituting. Dx is actually minus dz over 2z to the 3 halves, it is this. Times, sorry for this one, this should be dy. There is a dy over here. Okay? Times 1 over dy, okay? Minus 1 over 2y, okay? Oh, this is plus. Yeah, minus 1 over 2y plus 1 over the times the value of x. Value of x is actually 1 over the square root of z. I am just following this, okay? Equal to minus y cube over 2 times the value of x, which is 1 over the square root of z, all raised to the third power. We multiply this one, I just compress the first term, this should be minus dz plus 2z to the 3 halves times dy. dy is underneath, minus, okay, minus, minus 1 over 2y, the square root of z, I just compress this one. I will try to multiply this one, 1 cube is just 1 times y cube is y cube over 2, z to the 1 half cube. So what will come out will be z to the 3 halves. Okay? And to make the first term simply dz over dy, we multiply all the terms by the reciprocal of this. There's a negative, it should be plus, so we place a minus here. Minus 2z to the 3 halves. So actually the first term times this, what will come out will just be simply dz over dy. Okay? Second term will be plus z over y. Okay? I think they should be plus, guys. They should be plus. This plus. Okay? So this is plus. Sorry for that one. So actually this is minus. Okay? This will be eliminated. What will come out on the upper part, it will just be simply c. So it is plus z over y equal to the right hand side, this term here cancel with this. Okay, negative, this will now be y cube. So this is plus. This is plus. Okay. So after the substitution of dx and x, what comes out is actually case number 2 for a differential equation that falls under the solution by using integrating factor. And this is similar to the form dz over dy plus r of y times z equal to s of y. This is solvable by using integrating factor. The value of the integrating factor for this resulting differential equation is actually e raised to r of y. R of y is 1 over y. 1 over y. Because this can be written as just simply 1 over y times a. Okay? So the resulting integration of the exponent, it will become the integral of dy over y natural logarithm of y, the antilog of the natural logarithm of any given function is just a given function. So the resulting integrating factor is just simply y. We are just lucky what comes out will be a simple term. So if we try to bring out the solution now, it will be z times integrating factor equal to the integral. The right hand side is y cube, right? Times again the integrating factor times dy plus c. Luckily, the right hand side is just the integral of y to the fourth dy. And it is under the power formula. It should be 1/5 y to the fifth, right? So this is 1/5 y to the fifth plus c. But there is a z over here. But z is actually 1 over x squared. So the final general solution will be x squared over y equal to 1/5 of y to the fifth plus c. That's our general solution. That's it, guys. That is example number 3 under the solution of a Bernoulli's equation. So the first part of the solution is to rearrange the given differential equation. Then if you try to identify the value of n after the rearranging, you could compute for the value of z and you could compute for the value of x. Take the differential of x by using differentiation. Then take again the value of dx and x. We place back on the rearranged differential equation. It is this. This should be plus, guys. This is plus. This is actually dx. This is 1 over dy. Okay. We try to simplify. We multiply all the terms by this. What comes out is just simply dc dy plus 1 over y times z equal to y cube. Case number 2 under integrating factor. The integrating factor is e to the integral of r of y. R of y is 1 over y. This is the integral of 1 over y dy. The integral of dy over y is natural logarithm of y. The antilog of the natural logarithm of y is just y. So the resulting general solution, I will repeat it for the last time before we go this afternoon. Z times y equal to the integral of y cube, the right hand side, y dy plus c. Then replace z by 1 over x squared. Final general solution will be x squared over y equal to 1/5 y to the fifth plus c. That's it, guys. If you are taking differential equation and you are interested on the explanation of this, please subscribe to my channel. Thank you. Good afternoon, Los Angeles.